Hey guys, today we are going to learn a little bit more about pH, and we are also going to learn about neutralization. So when we left off last time, I had introduced the pH scale and introduced that it was a logarithmic scale. Now, if you remember, each time we went up a number in the pH scale, we went down by 10 times the concentration. So let's do the concentrations really quick on the pH scale. And I am going to just do this really quick. Let's see. So our concentration on a pH 0 would be 1 mole per liter, and 1 would be 0.1, and 2 would be 1 times 10 to the negative 2. And 3 would be 1 times 10 to the negative 3 in terms of concentration, and so on and so forth until we got all the way to 1 times 10 to the negative 14. So notice as the concentration gets smaller, 1 times 10 to the negative 4 here, and 5, and so on. As the concentration gets smaller, the pH number gets bigger. So the more concentrated that acid is, the lower that pH number is going to be. And the more concentrated the base is, the more high that pH number will be. Okay, so notice that I have a scale from green, and where it's green, it's pretty acidic. I'd say actually to 6, not to 5. Acidic. And then from 8 to 14, we have basic. Okay, that means this area in the middle is pretty neutral. Now, technically, only 7, like pH right on 7, is neutral, but pretty much anything from 6 to 8 is considered relatively neutral. Okay, so let's rank the following from least acidic to the most acidic. I think the easiest way to do this is to create a pH. So if I take a negative log of 1, I get a pH of 0 here. And this would give me, I have to move my decimal place 3, so this would give me a pH of 3. This is a pH of 2, pH of 10, and let's see, 1, 2, 3, 4, 5, 6, 7. So this would be a pH of 7. Okay, that makes it really easy. So which would be our most acidic? Would be our lowest pH. So what's our lowest pH here? 0. So this would be our most acidic. So this would be, let's see, it says least acidic to most acidic. So let's look actually at the highest number. So this would be least. So our scale would be pH of 10. And then our next one would be a pH of 7. So we've used that one, and then pH of 3. We've used that one, then pH of 2, and then our pH of 0. That would be our most acidic. So this would be least to our most acidic. All right? All right, so what is the approximate hydrogen ion concentration of the following? So if I look at ammonium, let's see, ammonia, we're at a pH of about 12. So pH of 12 would give me a hydrogen ion concentration of 10 to the negative 12. Okay, vinegar, let's look at that one. Vinegar is a pH of 3. So that gives me a pH of 3. So that would give me a hydrogen ion concentration of 10 to the negative 3. All right, so take a minute and do the rest of these, and let's check your answers with mine in a minute. Okay, sodium hydroxide is here at 14, so a pH of 14. So that would give us a hydrogen ion concentration of 10 to the negative 14. Human saliva is here at 7. So pH of 7. That would give me a hydrogen ion concentration of 10 to the negative 7. Bananas are slightly acidic, so they're at a pH of 5. So that would give me a hydrogen ion concentration of 10 to the negative 5. Normal stomach acid is about a pH of 2. So pH of 2. That would give me my hydrogen ion concentration of 10 to the negative 2. Upset stomach acid is about a pH of 1. That would give me a hydrogen ion concentration of 10 to the negative 1, or just 0.1. Okay? Antacids. So antacids are right here under borax. They're about 10 to the negative 10. So pH of 10. So that gives me a hydrogen ion concentration of about 10 to the negative 10. Okay. So why do you think antacids will help cure an upset stomach? An upset stomach is really, really acidic. It's got a pH of 1. And antacids have a pH of 10, which is basic. What happens when we mix an acid with a base? Think about it. They neutralize each other. So antacids are a base. And an upset stomach is acidic. When we put an acid plus a base, we neutralize them. And we make a neutral solution. Okay, so we're going to talk a little bit about neutralization reactions. So let's go on to that next page. So when an acid reacts with a base, we have what is called a neutralization reaction. So let me write a generic acid and base reaction for you. So if I have a generic acid, HA, reacting with a generic base, BOH, the hydrogen is going to get together with the hydroxide. HOH really is just water, right? HOH. Don't I have 2 hydrogens and 1 oxygen there? So water. Isn't water neutral? That's why we call them neutralization reactions, because we take the hydrogens from the acid, the hydroxides from base, and we put them together, it makes water. And that's neutral. And then we make an ionic salt, where B is usually some kind of metal or positive ion, and A is some kind of nonmetal or negative ion. So we make an ionic salt. Okay, where B is a positive ion and A is a negative ion. Usually B is a metal, and A can be a nonmetal or a polyatomic ion. So you are going to want to look at your polyatomic ion chart on page 63. This is going to help you. And remember the ions on our periodic table, okay? So we want to write down the following equations, which means that we are going to have to, 1, predict what's going to be made, and we're going to have to write formulas. And it's been a long time since we've written formulas, which means we're also going to have to be aware of the charges that we have. Okay, so let me get up our periodic table, because we're definitely going to want our periodic table here. So let's get this. Gen Chem, we want our periodic table. I can find it. And we probably are going to want our polyatomic chart as well. So let me see if I can get up the polyatomic chart. And that, the easiest copy I have is probably in the notes. Let's see. Periodic table and ions. Okay, we're going to want this second chart with the polyatomic ions. Okay, so we've got all the things that we need. So let's start looking at these reactions. So I have hydrochloric acid, HCl, reacting with sodium hydroxide. The first thing that I want to do before I even start writing down anything is I want to put in our charges. So I'm going to grab the periodic table. If you remember, everything in this first column right here was a +1. Everything in the second column was a +2, okay? And everything in this second to last column was a -1, and most things here were a -2, and some of these things were a -3. So we're going to use that to help us figure out the charges, and we're also going to use the polyatomic chart. So we had hydrogen. Hydrogen is in this first column, so it is a +1. Do you agree with that? So hydrogen is a +1. Chlorine's in this second to last column, so it is a -1. So I'm going to put those charges on here. So hydrogen is a +1, and chlorine is a -1. Okay? Sodium. Let's look at sodium. Sodium is also in this first column, so it is also a +1. But OH is a polyatomic. So sodium is a +1. Let's look at the OH really quick. Okay, so OH, let's see if we can find OH. OH is right here. It is hydroxide. It is a -1. Okay, so OH is a -1. So let's put that in there. Now remember, when we put compounds together, we have to have a positive bound to a negative. Okay? So hydrogen's already bound to chlorine. So what's the only other negative it can be bound to? That would be hydroxide. Hydrogen plus hydroxide, +1 plus a -1. That equals 0. Remember, the sum of the charges has to equal 0. So if I have a +1 plus a -1, that equals 0. So I just need one of each. So HOH, like I said up here, really makes me water. Okay, so I have made water. And then the only other negative that the sodium can get together with is the chlorine. +1 for the sodium, -1 for the chlorine. 1 plus -1 equals 0, so I just need one of each. So I will make sodium chloride, known to you guys as table salt. Okay? So remember, when we're doing these things, the very first thing always is to write the formulas. And by doing that, you have to look at the charges. Okay? Well, then that's what we did. And then once you've got those formulas written and you've got those charges all balanced out to 0, right? The sum of the charges have to equal 0. Then you go back through and then you balance the equation. Now, I'm going to do this one element at a time. I've got 2 hydrogens and I've got 2 hydrogens. I've got 1 chlorine, and 1 sodium, and 1 sodium. So this is balanced just the way it is. Okay? That means I have one of each, right? But in math and in chemistry, a 1 is always implied. So when you get to your homework, if there is a 1, you're going to need to pull 1 down from your drop-down menu. But when you write out the equation, we normally don't put 1s in there. Okay, let's move on to the next one. So we've already determined that hydrogen is a +1. So I'm just going to use that already. Each of those two hydrogens are a +1. Let's look at sulfate, SO4. That's on our polyatomic chart. So SO4. SO4, sulfate. That is a -2 charge. So let's put that on there. So sulfate is a -2. Okay? Now for potassium and hydroxide, we've already determined in our previous one that hydroxide is a -1. Okay, so we know that the OH is a -1. Let's look at potassium. Let's look at our periodic table. Potassium's right here. It's in that +1 column. So potassium has a +1 charge. Okay, so I've got potassium hydroxide. So hydrogen is going to get together with OH. I've got two hydrogens and I've got two OHs. So I'm going to make two waters. Okay, and then potassium, I've got a +1 and I've got a -2 in the sulfate. So how many +1s do I need to balance that -2? 2 times 1 gives me a +2. +2 minus negative or plus a -1 equals 0. So I'm going to need two potassiums. So remember, to do the two potassiums, we're going to do a subscript, and then we will put the polyatomic sulfate at the end. Remember, we always write the positive atom or ion first, and the negative ion always comes second. So the positive is always written first, the negative is always written second. Okay? So there we go. We've balanced the charges. Now, let's see. Let's balance the equation. 2 hydrogens plus 2 hydrogens here gives me 4 hydrogens. 2 times 2 gives me 4. I've got one sulfate group and I've got one sulfate group, so I'm good here. I've got 2 potassiums and I've got 2 potassiums. So this is balanced. Okay, now let's look at this next one, calcium. We've already said that we've got hydroxide, right? Right here. That's a -1 and a -1. Okay? So we've already done that. So we need to look up calcium and we need to look up lithium. So calcium is right here. It's a +2. And lithium is a +1. Okay? So calcium is a +2 and lithium is a +1. All right. Now, here we go. Now, both of these are hydroxides. So calcium, the only other thing that it can get together with that is negative is also a hydroxide. Is that really going to change anything? Not really. So, and a calcium is a +2, so hydroxide is a -1. So +2 plus -1 gives me +1 still. So I need one more negative. So if I do 2 hydroxides, 2 times -1 gives me -2. +2 plus -2 gives me 0. So I'm going to need 2 hydroxides. So calcium hydroxide. Oh, this is not wanting me to write. And lithium is a +1, and hydroxide is a -1, so they just need one of each. Okay, did we change anything? We didn't neutralize anything. That is not a neutralization. because having a neutralization, we would always make water. We didn't change anything at all. Okay, so remember, when we are doing a neutralization, we are always making water and some kind of ionic salt. Okay, all right. So if I had a pH probe and I was actually able to do pH on my y-axis as I added, this is as I add base. So notice this is measuring the volume. So the more volume I add, this is how the pH changes. Okay. Now, when we look at these pH titration, these are called titration curves, by the way. When we look at them, we always want to look in the middle of this very steep thing. So right dead in the middle is what we call the equivalence point. That's the point where we have equal acid and base. Notice here, if I have, this is a strong acid with a strong base. Notice my equivalence point is right at pH 7. So if I have an equivalence point with a strong acid and a strong base, that equivalence point will be neutral. It will be at a pH 7. Okay? But pH is not always at a 7 when we have that equivalence point. So the pH after neutralization is not always a pH 7. It's not always neutral. So let's look at what happens when we have a strong acid with a strong base. This one right over here is where we are adding an acid to a base. Okay? Let's look at that middle of that really steep curve. So if we look at that middle, we are at a pH 7. So pH 7, strong acid, strong base will always give us an equivalence point at 7. But let's look at what happens when I have a strong acid added to a weak base. Okay, so if we look at halfway on this equivalence point or this inflection point, my equivalence point is a pH less than 7. So think about this. If you have a really strong kid playing with a weak kid, isn't the strong kid going to dominate? So yeah, because the acid is strong and the weak is base, the acid is going to dominate. So our equivalence point is actually going to be in the acidic range because the acid is stronger than the base. Remember, strong means it dissociates 100%. Okay, so this acid will dissociate 100%. This stays together and doesn't dissociate that much. So we're going to have a whole lot of extra hydrogens around in that solution. That's why we get an equivalence point that's actually in the acidic range. Okay? So what happens when we have a weak acid with a strong base? Okay? So look at the midway of this equivalence point is right about here. Our pH is greater than 7. So our equivalence point is in the basic range because that strong base is going to be overpowering to that acid. So that means we're going to have a whole lot of extra hydroxides out in solution. So it's going to neutralize in a basic range. If I have a weak acid and a weak base, notice we don't get any really strong inflection point at all. You just have to kind of go what's like in the middle of this curve, which makes it really hard to see, which is about here in terms of height. And we are at about a 7. Okay? So whether we're titrating a weak or strong acid against a weak or strong base totally determines the shape of that curve and where that inflection point on that curve is going to be. So just know that if I have a strong acid with a strong base, that will be a neutral titration. If I have a strong acid with a weak base, it's going to end up acidic. If I have a weak acid with a strong base, it's going to end up basic. All right, so there you have it. That's our range of pH and how we look at neutralization. Have a great day, and we'll talk to you later. Bye.